Welcome back to the channel. Today we're diving deep into one of the most fundamental concepts in AI and machine learning, tensors. If you've ever wondered what's really happening under the hood when neural networks process data, this video is for you. By the end of this video, you'll understand exactly what tensors are, why they're crucial for AI, and how to work with them in popular frameworks like PyTorch and TensorFlow. So grab your coffee, hit that like button, and let's get started. Let's start with the basics. What exactly is a tensor? Think of tensors as containers for data, but not just any containers. They're like mathematical Swiss Army knives that can hold numbers in multiple dimensions. A scalar is just a single number, like the temperature outside, which might be 25 degrees. That's a zero-dimensional tensor. A vector is a list of numbers, like your daily step count for a week. 8,000, 12,000, 6,000, 9,000, 11,000, 7,000, 10,000. That's a one-dimensional tensor. A matrix is like a spreadsheet, rows and columns of numbers. Imagine a grayscale image where each cell contains a brightness value from 0 to 255. That's a two-dimensional tensor. But here's where it gets exciting. Tensors can have 3, 4, 5, or even more dimensions. A color image, that's a 3D tensor with height, width, and color channels. A video, that's a 4D tensor adding time as another dimension. Think of it this way. If a matrix is like a piece of paper with numbers, a 3D tensor is like a stack of these papers, and a 4D tensor is like multiple stacks arranged in a grid. Now, you might be thinking, okay, but why should I care about tensors? Here's the thing. Every single operation in modern AI happens with tensors. When you feed an image to a neural network, it gets converted to a tensor. When the network processes that data through layers, it's performing tensor operations. The final prediction? Also a tensor. But it's not just about data structure. Tensors enable parallel processing. Instead of processing one pixel at a time, we can process entire images or even batches of images simultaneously. This is what makes modern AI training feasible. Your GPU has thousands of cores designed specifically for tensor operations. Without tensors, training a model like GPT or ResNet would take months instead of days or weeks. Think about it. When you're training on a batch of 32 images, each 224 by 224 pixels with 3 color channels, you're working with a tensor of shape 32, 224, 224, 3. That's over 4.8 million numbers being processed simultaneously. Let's get technical for a moment. Understanding tensor rank, shape, and dimensions is crucial for debugging and designing neural networks. Rank is simply the number of dimensions a tensor has. Rank 0, scalar, just the number. Rank 1, vector, 1D array. Rank 2, matrix, 2D array like RGB image. Rank 3, 3D array like RGB image. Rank 4, 4D array like a batch of RGB images. Shape tells us the size of each dimension. A shape of 3, 224, 224 means 3 color channels, 224 pixels height, and 224 pixels width. Here are some shapes you'll see constantly in AI. Image, height, width, channels, 224, 224, 3. Batch of images, batch, height, width, channels, 32, 224, 224, 3. Text sequence, sequence length, embedding dimension, 512, 768. Batch of text, batch, sequence length, embedding dimension, 16, 512, 768. The magic happens when we reshape tensors. A 224 by 224 image can become a vector of 150,258 elements or be reshaped for different operations. Understanding these transformations is key to mastering AI. Let's trace how tensors flow through a typical neural network. This is where everything clicks together. Step 1. Data preparation. Your raw data, whether it's images, text, or audio, gets converted into tensors. A batch of cat photos becomes a 4D tensor of shape, batch, height, width, channels. Step 2. Forward pass. Each layer receives a tensor, performs operations, matrix multiplication, convolution, etc., and outputs another tensor. Watch this. Input 32, 224, 224, 3. After conv layer, 32, 112, 112, 64. After pooling, 32, 56, 56, 64. After flatten, 32, 2704. After dense layer, 32, 1000. Final output, 32, 10 for 10 classes. Step 3, backward pass. During training, gradients flow backward as tensors too. Each gradient tensor has the same shape as its corresponding parameter tensor. The beauty is that all 32 images in our batch are processed simultaneously. That's the power of tensor operations, massive parallelization. Now, let's talk about the operations that make AI tick. These tensor operations are literally the building blocks of every AI model. Element-wise operations. These happen between corresponding elements, adding two tensors of the same shape, applying activation functions like ReLU, or computing square differences. Matrix multiplication, MapMult. This is the heart of neural networks. When data passes through a dense layer, it's matrix multiplication happening. Convolution operations, essential for image processing. A small filter slides across the input, computing dot products. Reduction operations. These collapse dimensions, like finding the maximum along an axis, or computing averages. Broadcasting. This lets us perform operations between tensors of different shapes. A tensor of shape 32 by 224 by 224 by 3 can be added to a tensor of shape 3. The smaller tensor gets broadcast to match. Let's see tensors in action across different AI applications. This is where theory meets reality. Computer vision. In image classification, a photo becomes a tensor, passes through convolutional layers, tensor operations, and produces class probabilities, another tensor. Natural language processing. Text becomes token tensors, passes through transformer layers, attention is tensor operations, and generates new token text. Time series analysis. Sequential data becomes 3D tensors, batch, time steps, and features, processed by RNNs or transformers. A PyTorch example. Let's get hands-on. PyTorch makes tensor operations intuitive and Pythonic. B TensorFlow example. TensorFlow has a slightly different syntax, but similar concepts. Here's a simple neural network showing TensorFlow. Working with tensors can be tricky. Let me share the debugging techniques that have saved me countless hours. 1. Always print shapes during development. 2. Common shape errors in solutions. 3. Understanding broadcasting. 4. Performance optimization. Let's explore some advanced tensor concepts that you'll encounter as you dive deeper into AI. Automatic differentiation, AutoGrad. This is how neural networks learn, by computing gradients automatically through tensor operations. Tensor parallelism. For large models, we split tensors across multiple GPUs. Sparse tensors. For tensors with mostly zero values, sparse representation saves memory. Quantization. Reducing tensor precision for faster inference and smaller models. Wow, we've covered a lot of ground today. Let's recap the key takeaways about tensors in AI. Key takeaways. 1. Tensors are the foundation. Every AI operation works with tensors, from data input to final predictions. 2. Shape matters. Understanding tensor shapes and dimensions is crucial for debugging and designing networks. 3. Operations are building blocks. Element-wise operations, matrix multiplication, and convolutions are the core tensor operations powering AI. 4. Frameworks make it easy. PyTorch and TensorFlow provide intuitive APIs for tensor manipulation. 5. Think in batches. Modern AI processes multiple examples simultaneously for efficiency. 6. Debug with shapes. Always print tensor shapes during development to catch errors early. And 7. Advanced concepts. Autograd, parallelism, and optimization techniques unlock the full power of tensors. What's next? Start experimenting. Create tensors, perform operations, and build simple neural networks. The best way to understand tensors is to work with them hands-on. If this video helped demystify tensors for you, smash that like button and subscribe for more deep dives into AI concepts. Drop a comment below with what AI topic you'd like me to cover next. Thanks for watching, and I'll see you in the next video. Until then, keep learning.